questions that have come up? Okay, so let's get into this. All right. This is where we ended yesterday. We had talked about the how ubiquitous both carboxylic acids and their respected salts biochemically. You see them in ice cream, medicines, etc. All of you have heard of citric acid. That is a interesting acid. It's a triprotic acid, meaning it's got 3 hydrogens that can come off. It's also an alcohol. So it undergoes lots of different kinds of reactions because it's got a plethora of functional groups that can interact with other things. Now, if we add an alcohol to an acid, we get a new functional group called an ester. Okay, the side with the carbonyl group is the acid side. There. The side, and then the other side of the oxygen would be the alcohol side. And when we're naming these things, we have to talk about both the alcohol and the acid as part of the name of the ester. It is the chemistry of lipids. Lipids are found all over the body biochemically, found in membranes, they're found in energy storage, plus they're linked with other groups such as alcohols and carbohydrates as well. Now they range from 1 to 26 carbons for the acid side. For the alcohol side of the ester, you can also get a very long alcohol. In fact, when you have a really super long acid and a super long alcohol, that's defined as a wax. Esters can be very volatile. Hence, you frequently see them around perfumes. When you're cooking, you frequently will smell an ester. When you're tasting food, you're frequently tasting an ester. Now, the process of forming an ester is called esterification. And now these can be aliphatic or aromatic alcohols. Okay, under acidic conditions with some heat, the alcohol and the acid form a COC bond series. and we end up generating water. And then the reverse reaction requires water, actually. And then it repopulates the hydrogens on the alcohol and the carboxylic acid that were left when the ester is formed. Now, notice there's an R and an R prime. All that means is R is some kind of a carbon chain, and R prime is a carbon chain, but it's not necessarily the same as R. It's just different. You can also have R double prime as well. Okay, so let's take butanoic acid, 4 carbons, ethanol, 2 carbons, and this guy is going to go there. So we end up with and we're going to talk about naming in a minute here. You're going to see in the lab, when we do a lab with esters, you're going to find that this acid here, butanoic acid, is extremely smelly. So saying on Monday, that's what gives rancid cream, rancid butter, cow patties. That smell is the butanoic acid, or butyric acid, it's usually referred to. Once the ester is formed, however, that fragrance, you call it that, is totally transformed. So we're taking a extremely stinky acid and making it into a very pleasant strawberry flavor and fragrance. Excuse me. Another example would be, this is salicylic acid. It's one of the main components of aspirin. When we make aspirin in a number of labs away, we're going to be using salicylic acid and a form of an alcohol to make aspirin. But if you take just plain old methyl alcohol, it's going to add to the acidic part of salicylic acid to form methyl salicylate, which is oil of wintergreen. All of you have had wintergreen gum, I'm sure. Anyway, it's very easy to make. So salicylic acid also is a solid, and this ends up being a liquid. So the physical characteristics of an ester sometimes can be quite different than the parts that put it together. And let me, so this is the acid part. We're going to be naming the yellow acid part and the alcohol blue part. Both have got to be contained in the name. I'm going to talk about in a minute here. There are 2 other ways to make esters. Okay, the first one is starting with the acid, and then which gives the least yield. The acid chloride gives the most yield. And the anhydride is intermediate. This is a very unstable. So its shelf life is very short. Most of the time, people don't use the acid chlorides to make esters. This is stable shelf life wise, but it gives the least yield. Hence, they usually use the anhydride, and that's what we're going to use when we make our aspirin. We're going to be using the anhydride. So we're going to use the acid chloride in place of the acid. So here's the quote unquote acid part. And this is going to be the alcohol part. That's the acid part. Alcohol part. And then notice this yields hydrochloric acid, and this yields another one of the acids. Now, I'm going to talk about this anhydride. It looks like a goofy looking molecule. Look at a really simple anhydride. Think of this as two esters. When an ester loses its alcohol, it forms its originating acid. So when this side reacts, it loses the right side, and the left side reacts with the alcohol, like the original acid. It kicks this piece off here, and that piece is going to be the exact same acid as the other side. So if we started with an ethanoic acid here, we're going to end up with generating an ethanoic acid there. So when this reacts, we've got this piece. Let's say we're adding, I'm going to do, let's see, let's add ethanol. So what we're going to generate is a 2 carbon and 2 carbon. So we're going to end up looking like this. Plus this over here. So the anhydride is the preferred way to make an ester because it's fairly stable and it also gives decent yield. Starting with the original acid gives very poor yields. Using the acid chloride gives great yields, but it's a very expensive product because its shelf life is so short. It gives really maximum yield. Okay. So again, just think of the anhydride as 2 esters stuck together. Okay. So here's the acid piece of the acid chloride. Here's the alcohol. What's left over is HCl. Okay, if we're looking at using the anhydride, we have the acid here, alcohol here, and then we kick off this as an acid here. Let's do that in green. Now, yes, it does have to be have an OH on it to be an alcohol. I'm just saying the part of the ethyl alcohol becomes part of the ester, and this is the piece here. I'm not sure what your question was. All alcohols, by definition, have to have an OH group in it. Here's the OH group here. This is no longer an alcohol over here, though. This OCC came from the alcohol, but it's no longer an alcohol. Was that the basis of your question? Okay, better now? Cool. All right. Okay, so let's talk about naming these guys. I don't know where the slide is on naming. Oh, it's right there. Okay, we're not doing polymers except for biological polymers, which is going to be unit 3 when we talk about amino acid polymers, aka protein. So we're not going to be doing polymer stuff. Okay, so to name an ester, now if we have a three-carbon acid, that would be propanoic acid. If we have a three-carbon alcohol, that would be propanol. So we're going to be adding these two together for the ester. The first part is going to be going to be naming the alcohol part of the ester. Okay. So that would be propyl. And then the second part, we need to name the acid part of the ester. And that we're going to add a eight from the acid part. So this is going to be propyl, propa, So purple comes from the acid part. So let's do this in colors here. So naming ester is in two parts. We name the alcohol part, the original alcohol part, like it was a branch. Then we name the acid part like it was the salt of the acid, adding an ATE. So alcohol part, acid part. So to name this, we would name it as methyl. Let's not use the acetate, let's use the IUPAC name. This is the alcohol part of the name, acid part of the name. Now, ethanoate is usually referred to as the common name derived from acetic acid. They call it acetate. You can use either one in this class, unless I asked you for the IUPAC name specifically in a test question. Okay, does this make sense? All right, so let's name this guy here. Okay. All right, so this is going to be named the alcohol part first, so it's going to be phenol. And we name the butanoic acid butanate, butanoic. Easy to pronounce, huh? This one would be ethyl. Benzoate. Now you can have branching on this stuff too. For example, let's do one here with branching. Let's take the acid chloride and let's add in ethanol. Okay, so now we're going to start with the acid side. Okay, so how will we name these guys? Well, this would be ethanol. Acid chlorides, acid chlorides are named a bunch of different things. We're not going to worry about naming the acid chloride in this class. You could name it probably the most commonly seen. There's a lot of different ways to name it. So propanoic chloride would be the most straightforward way to name this. Okay, and then what do we have over here? We have the branch on that acid. Now, first thing we have to do is name the alcohol part. Alcohol part of the ester. So that's going to be ethyl. And then the acid part is going to be 1, 2, 3. Let's see. It's going to be 2-methyl. Propanoid. Okay, so this is the alcohol part. And this is the acid part. And we can do the same reaction using the anhydride. The anhydride is going to be 2 esters of the acid. Oops. Well, actually, this would be 2-methyl. I forgot about the branch. Okay, propanoic chloride. Okay, so this is going to be 2-methyl. And anhydrates can use, these can be different acids for the anhydride. In this class, they're always going to be the same. They can be different. In fact, we're going to see when we get into biochemical esters of phosphate, where we have the phosphoric acid and a ribose sugar forming an ester, and in a subsequent slide. Okay, so we're having the anhydride plus ethanol and here's our acid. Plus the leftover, let's do that in here. Okay, so we could have also started with the acid, plain old acid. give the ethyl 2-methyl propionate. So the three methods here. Now you need to know these three methods. This is the preferred one because of okay, so the preferred one is the anhydride because the anhydride stores better than the acid chloride. The most stable of the three is the starting with the acid, but you get a poor yield because the acid is so much more stable than the ester it creates. But all three of these will produce that ethyl 2-methyl propionate. Okay. Now we can take apart an ester as well. In an acidic environment, in water, it'll break apart into its original acid and its original alcohol, whether that's aromatic or aliphatic. The enzyme Kase takes apart fats. So it breaks down so we have a fat, which is something called a triglyceride. I'm going to talk about that when we get into lipids. The triglyceride is made up of three esters. In the presence of lipase, the lipase will convert those three esters into three fatty acids plus glycerol is the acid or the alcohol, I mean. So we look at an ester, again, we need to look at its parts. Originally, this was the acid part and the alcohol part. So when it breaks up, it's going to break up into its original acid and original alcohol. Notice here, no heat is required, just acidic environment. Acid, alcohol. Acid, alcohol. So, the two-way street. Acids form, esters form, esters break apart, form, break apart, form. Now, this was in an acidic environment. Oops. So that acid is protonated in an acidic environment. In an alkaline environment, we form the salt of the original acid. Okay, so saponification is where they get the word soap from. Saponification is when we break up an ester in an alkaline environment. So if I give you a molecule and ask you, can this be saponified? First thing is, is this saponifiable? It needs to have an ester present, and it has to be in an alkaline environment with pH greater than 7. Okay, so when we make soap next week, we're going to start with fat, which is an ester. We're going to put it in an alkaline environment, also known as lye, and we're going to make soap with it. Now, this reaction seems like it goes pretty fast, but actually it's a very slow reaction. So it literally takes months to fully form soap. It may look soapy and it'll make suds and stuff, but it's not fully cured soap. If you get it in your eyes, for example, it really hurts because there's lye there. Okay. Acid, acid. Alcohol, alcohol. So methyl means we started with methanol. This is the sodium salt of benzoic acid. We started with KOH would work just as well. That would be the potassium salt of benzoic acid. When we have the ionic form of the acid, we go to the ATE form of the name, benzoate. Sodium benzoate is a common preservative used extensively in preservation. Okay, so right here we have a saponification. 1, ester. 2, pH greater than 7, because lye is a strong base. This is the mechanism by which this works, which we're not doing mechanisms in this class. If you take the year-long organic chemistry with no biochem, it's just pure organic, you are immersed big time in mechanisms. You know, you have electrons going around, you have nucleophiles, electrophiles, and carbocations, carboanions, and it absorbs the class besides reactions. Okay. So, looking at acids and esters. Okay, if you start with an acid, you can put it just in plain water and it'll disassociate. what that means is you end up with a proton coming off. Carboxylic acid in the presence of an alcohol forms an ester, which can come apart in acidic environment, and depending on what you start with, you'll end up with the acid and the alcohol. It's in an alkaline environment, you end up with this acid salt and the alcohol. Okay, so these are the acids you need to know. Some of these you probably already know. Half of them you probably don't know. Now there's two ways of, are there any questions regarding ester reactions? Let's see what the chat says. Is why did you get rid of the methyl? What example were you talking about? This example? What example were you talking about getting rid of the methyl? Because I'm not sure.
It was like way before, like you just wrote it and you didn't have the methyl on it, but then you added it. So it doesn't matter anymore.
Okay, so I kind of answered your question earlier.
Yeah.
Good. Okay. All right, so let's go down to acids now. Okay. I'm sure most of you have heard of oleic acid. You've probably heard of linolenic acid as an omega-3 fatty acid. You need to start calling it the alpha linolenic acid, however, because there's a gamma linoleic acid, which is not omega-3, it's omega-6. Stearic acid, palmitic acid is tied up in palm oil. It's a 16 carbon acid. Arachidonic acid is very important. Is it makes something called a prostaglandin. It's a precursor to a prostaglandin. Prostaglandins is how NSAIDs work. Non-steroid. NSAID is non-steroidal drug. What does the AI stand for? I have a block. Oh, anti-inflammatory is the AI stands for. So there's steroids and there's non-steroid anti-inflammatory drugs. Okay, Anyway, this arachidonic acid is a precursor to things like a pain relief. However, there's some side notes to that as well, where it produces things like anti-clotting. So if you have a tendency that if you have an ulcer in your stomach, you should not be taking NSAIDs because it'll incite it to bleed. Let's see, there's a number of other things anyway. And there's two pathways, and the new NSAID drugs work on inhibiting one but not the other. One produces bad effects, the other produces good effects. Anyway, this is the precursor to that. Okay. Okay, so let's take this nomenclature apart. Let's look at linoleic acid. Mostly comes from corn oil. Okay, so it's 18 carbons long. And it has two double bonds at positions 9 and 12. Okay, so let's draw this. Okay, so we're going to go so that's carbon number 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, double bond. 10, 11, 12, double bond. 13, 14, 15, 16, 17, 18. Okay, so this would be 18 to delta 9, 12. So these count from the acid end. This is also an omega-6 fatty acid. It starts from so this says the first encounter of double bond. So this omega-6 is used for dietitians, is used in the food industry. Biochemists don't use that. Biochemists use this one because this is one on the left here in blue because it has more information. It tells you, and not only it's 18 carbons long, 2 double bonds, and there are positions 9 and 12 relative to the acid end. So food, fitness industry uses the omega designation. Okay, so you need to know also the name of this guy. So to name this, it's going to be octadecta That's 8 plus 10, 9, 12 dienoic acid. And I'm going to put dashes in there too. Okay. The abbreviation for linoleic acid is LA. Biochemists use abbreviations a lot. So anytime there's an article, they'll define it right at the beginning of the article, and then they'll have LA, LA, LA from then on. ALA. When you buy omega-3 fatty acids, frequently you'll have this guy and this guy in the bottle. And those are longer yet. And they have a lot of double bonds. A lot of double bonds. A lot of double bonds. Okay, so this is Flashcard City. By the way, on so there's also, I was saying before, a gamma linolenic acid, GLA, and that is an omega-6. So the ALA is the sought after one. Now it's easy to get omega-6s, omega-9s in the diet. It's much more difficult to get omega-3s because usually those are found in flax seed oil and also in dark fish flesh. Those are the ones that cruise, like salmon, mackerel, and they have that dark streak running down the side. And everyone, when they eat salmon, they always scrape that off. That's where all your omega-3 fatty acids are, you're scraping off. Okay, so anyway, these are the fats you need to know. Okay, and there is a, let me just double check really fast. I'm checking for the paper that I just showed you on the acids you need to know. Well, I can't find it real quickly now. What I'll upload that to files unit 2. Okay, let's. This here guy, I'll upload that. Okay, now, when we talk about esters, we need an alcohol and an acid. Now, the acid part doesn't have to necessarily be an organic acid. It can also be an inorganic acid, like phosphoric acid. Phosphoric acid is used in our bodies a fair amount. It's the predominantly, for example, in a membrane, you have phospholipids. Okay, so you can form an ester by taking the alcohol part and the acid part. So this would be the acid part. And this is the alcohol part. So here is the ester. Now, notice phosphoric acid has got, it's called a triprotic. Meaning that 3 of the acids can come off. Hence, it's got 3 OH groups. That means you can form esters with itself. What happens is each one of the OHs can form an ester. And because we have 3 OH groups, we can form 3 esters. And the R's can be the same or they can be different. So there's R, R prime, R double prime. Now, when we get into glycolysis, one of the early steps of glycolysis, starting with glucose, is a phosphorylation of this is carbon number 6. And carbon number 6, we form a phosphoric ester, carbon number 6. And we're going to look at that in detail when we get into glycolysis in unit 3. The phosphoric acid can form a double ester, looking like an anhydride to some extent, and a triple one. For example, in ADP, ATP. That's the double phosphate ester, triple phosphate ester. And all of you know that ATP and ADP are energy sources for our bodies. When it goes from ATP to ADP, loses a phosphate group and lots of energy is given off. So this is what ADP looks like. Now, a couple things here now. That is ribose, sugar. And this is adenosine, which is one of the base pairs and a DNA backbone. So what ties backbone together in DNA and RNA is phosphate esters. Now, this would be ATP, ADP. This would be the one that comes up to form ADP. Okay. When we have a DNA molecule, So DNA is made up of three parts. There are the base units, ribose or deoxyribose, depending whether it's RNA or DNA, and phosphate esters linking the ribose sugars together. So this inorganic phosphate ester is really important biologically. We have things like ATP, ADP, we have DNA, RNA, all stuck together with a simple sugar ribose and phosphate esters. So when you get into DNA replication with the tRNA, the mRNA and stuff, what it's doing, it's either forming or breaking these phosphate esters. Okay, so that is it on carboxylic acids and hydrides. Okay, are there any general questions about this chapter?
So for the chart that we had for the esters and the reactions that they undergo, will we be given the chart on the second exam?
Which
It was way up. Yeah, this one, yeah.
yes.
Okay, thank you.
Yeah, you'll have this. I like to give you the charts. So you can use it to figure out how you're going to synthesize something. For example, if you're going to synthesize an ester, okay, how do you synthesize an ester? Well, you need an alcohol and an acid. And the acid can be in the three forms, the anhydride, the acid chloride, or the original acid. What happens with an ester in a base? You get that says saponification. I think I'd rather read it more carefully. Get saponification, that kind of stuff. So, yeah, I'll supply that. And then this guy, you guys need to know. What are their 8 acids here? And I'll put that on under Unit 2 files. Okay, any other questions? Okay, I want to do the intro to lipids. Yes, you can come to the Wednesday lab, Caitlin, and lab 3 is due tonight by midnight. It's always on a Wednesday it's due. Now, the chemistry of lipids is the chemistry of acids and esters. Most of you have a pretty good handle on lipids in our world in terms of what they're used for, energy sources, formation of cell membranes. Cell membranes are how the body can separate aqueous reactions from another aqueous reaction by putting non-polar barrier in between those two, and that's called a membrane. Remember, once we get past 7 or 8 carbons, the intermolecular forces of that long carbon chain take over. Even though acids are very polar, but once we start adding on those really, really, really long carbon chains, the carbon chains take over the physical properties of that fat. Okay, so lipids can be divided basically into 2 parts. Saponifiable, meaning there's an ester present, and no ester. Here's that prostaglandin coming up again here. Okay, once we know it's an ester is present, there are simple ones, complex ones. Complex ones have extra stuff in it. Besides, the waxes and triglycerides are just carbon, hydrogen, oxygen. Once we get into the phosphoglycerides and sphingolipids, they add in usually phosphorus, sometimes nitrogen. So we have P and N present. Okay, I'm going to show you the difference between a triglyceride and a wax in a little while here. Okay, fatty acids, like the ones I want you to know, are the building blocks in lipids, except for the non-saponifiable ones, the steroids and the prostaglandins. All others, fatty acids are very stable there. There are also fatty acids in the other one, but not as common. And again, this is carbons greater than 7. Once you get greater than 7, the nonpolar tail takes over the physical characteristics of the molecule. When we have a molecule that has a water-soluble and a water-insoluble part on it, doesn't have to be long and skinny, as long as it's water-insoluble, water-soluble, we form in water. So this would be a polar So what happens is to form a stable state for a molecule that has polar and nonpolar parts, what happens is forms like a wagon train in the Old West. The reason why they formed into circles was for protection. Okay, with a molecule that has both polar and nonpolar parts, it does something similar. And don't forget, this is 3D. So what happens is it puts the most friendly parts on the outside to protect the non-friendly parts. So non-polar parts do not like polar solvents. They like a non-polar solvent. So if we did this whole thing in, for example, pentane, what would happen is you'd have and this would be the polar interior. So the same process would go on, it's just that would be turned inside out, so that the solvent-friendly parts are bathed in the solvent that they're most compatible in. The non-compatible parts are in the inside, away from the solvent. Okay, so you just turn this inside out. We reverse the polarity of the solvent to form the most stable state. It would be polar parts inside, non-polar parts on the outside. Does that make sense? And these are called micelles. Interestingly, what do you do if you just had a fatty steak, all that marbling in between the myoglobin and the muscle? What happens to that fat? How does it get into your body, since our body is mostly water? Well, to transport something that's not soluble, what you can do is surround it by something that is soluble in that water, which would be like a micelle. So this is water, and we're transporting that fat around the body. If we form it into a micelle, we can actually move it through a polar solvent, even though the main part of that molecule is non-polar. It's a clever way to do it. Okay. Fatty acids, and this can go up to 24, are straight chains. They can be saturated or unsaturated, and they have an even number of carbons. And the reason for that is we're going to talk about metabolism of lipids in unit 3, and it's made in 2 carbon units. So whenever you see a fatty acid in a in vivo in a body, it's an even number. And they can have double bonds. And they're usually in a cis configuration, usually. Not all the time. So you can have trans fats that are generated within our own bodies. These 4 are the most common we run across fatty acids. And each one of these has a delta configuration as well. This one's 18,0, so the delta 0. This is an 18 with 2. This would be 18.3, and this would be 18.1. Each one of these has a corresponding delta. Now, if you remember, whenever we have a, excuse me, whenever we have a cis in the long straight chain, it's going to kink the backbone. And depending on how many of these you have in a row, it's kinked even more. So this has got so this has two cis's, this has one cis, this has 0. So whenever you see membranes in a biological body, they usually don't have them kinked like this. They usually they're straight. As you probably be able to guess, the longer the fatty acid, higher the melting point, higher boiling point. As soon as you start adding double bonds, the difference is dramatic. For example, vegetable oil is liquid at room temperature. These guys are solid at room temperature. And we have some of these tend to be starting to get soft at room temperature. And then look at these. As soon as you get into the multiple double bonds, they're very liquidy. Notice oleic acid, 13 degrees C. That's why when you put your olive oil in the refrigerator, it turns solid. When you take it on the room counter, it's liquid. There's a whole series of essential fatty acids, essential amino acids. Those are the ones that our body has trouble making. And so we usually have to obtain those externally. Linoleic, linolenic are the two main ones. Linoleic is an omega-6, linolenic is an omega-3. Biologically, these are used all over the place. One of the main areas fatty acids are used is membranes, because our body cannot function, period, without membranes. And these make up the vast majority of membranes, along with a 3-carbon backbone, and usually a phosphate group ester in there as well. Usually fats are animal, room temperature. Oils are, and usually, again, there's exceptions to these guys. Plant and animal sources. Liquids, your vegetable oil, when you buy it, is not solid, it's very liquid. And high degree of saturation for fats, high degree of unsaturation for oils. Okay, I'm going to end this here. This is where we started getting at the nitty-gritty of all this stuff. Just real quickly, okay, for that ester to form, we need an acid, and we need an alcohol. So this glycerol has 3 OH groups on it. That's why we can form an ester. And this is called TGs. When you get a metabolic panel on your blood test, one of the which includes the lipid panel, you'll see a TG on there, and that stands for triglycerides. That's an important value, by the way. They'll talk about LDL, low density lipoprotein, and there are 2 forms of that. There's a high density and low density lipoprotein, and the blood test doesn't distinguish it. But if you look at TGs, that directly relates to the low density lipoprotein, which is the more dangerous of the low density lipoproteins. So TG is an important parameter in your blood test. Okay, so how are you guys doing?
It's a lot.
Yes, it is. I'm thinking about having a take-home portion of the test too, also. Whenever I have take-home tests, you have full use of your notes. The only thing I request that you work by yourself and not in a group. Okay, next week we're going to be making soap. Soap is when we take that triglyceride I just showed you apart in an alkaline environment. In other words, we saponify the triglyceride. Once you saponify the triglyceride, you end up with the salts of the acids that were attached to the backbone. And that is the soap. And the problem is it takes many months to cure. So we're going to make soap next week, but we're going to store it in our drawer, or actually we can store it in the lab rather than the drawer, till the end of the semester. And then you're free to take it home then. If you want to take it home next week, just don't use it till the end of the semester. You're free to do that as well. It's kind of a cool lab. It's pretty straightforward. Basically, we boil fat. I gave you the take-home part early, probably because the take-home would be due at the end of the test. I'd probably give you test is on the 23rd or the week of the 23rd. So I'd probably give you 3 or 4 days on the take-home part. And I would post it and then send out a message to everyone. Okay, any other questions? Tutoring. I mean, other than the working in a group, a study group is extremely important. You can always ask me questions. There is peer tutoring. I'm not sure how the peer tutoring works online. There's also programs at Sac City. One program, for example, is MESA program, MESA. And there are other programs that have study help and for various groups. that work out well. Mesa is an example of one, but there are 3 or 4 others. One is an Asian focus, another is an African American focus, just various focuses that offer tutoring as well. So I didn't really answer your question directly, but I hope that helps a little bit. All right, everyone, I will see you in a little while. We're going to be Wednesday lab, folks. We have to check into our drawers really fast today. So I have a method I'm going to be using for that. So anyway, take care all.